Thank you for joining us today. I'll be discussing the correct instruments to locate bad consolidation, voiding, delamination, and other defects in concrete structures. To get to that discussion, I'll begin by explaining a little bit about sonic and seismic testing. I'll also discuss where ground-penetrating radar, which as probably the most commonly used scanning and inspection tool, can be applied to void detection and poor consolidation and defects. Then we'll go on to specific applications, going through finding large or small areas of voiding, thicknesses, and more specific defects, such as how you might look for voids in various forms of post-tensioning ducts. So to begin, we need to think about how to plan out a project where voiding's involved. It might be that there was, during a visual inspection, some signs of external voiding, such as visible delamination or spalling when formwork is removed, or visible cracking on a structure, which we'll also address as we talk. Or it might be that there is the requirement to plan for voids location as part of quality assurance. So if you're using in-place permanent formwork, sacrificial formwork, it may be appropriate to use some of the tools I discuss here, or other tools to locate voids in them. And if you're doing precast, again, your off-form finish is probably very good, but there's maybe some scope to look for voiding there. And another area I'll call out is voids not within a concrete structure, but behind or as part of joining that concrete element onto other elements. So particular examples would be finding proper support or proper grouting behind tunneling or excavation with supporting walls, or finding voids within grout of precast duct, grout of rebar ducts or tension ducts. And also how you might go about finding cold joints in structures. Once you've got an idea of what your scope of inspection is, then it's appropriate to think about what tools to use, where and how those need to be applied on site, and what forms of documentation, data logging, traceability you'd require to make the best use of the information you do collect. And also what the output of the project would be. It may be as simple as marking up regions of risk physically on the structure, or it may be that a full report reference to drawings would be required. So this is the kind of considerations that go into making a prospect as this. One thing I would bear in mind when looking at projects where voids become relevant is I'm going to talk about a range of approaches today. Broadly, most of the tools I'm going to be discussing are various forms of sonic or seismic testing. 2 is always better than 1 when it comes to non-destructive tests, especially if there's only limited scope for destructive confirmation of the testing. Because if you use a single tool and you get a result that indicates there's a potential void, that's one point of information. If you've used a complementary tool, which also sort of confirms that region of question, it's a great way to provide more evidence and to have some certainty when two different techniques say the same thing, and to better target the disruptive portion of an inspection. So before we go on to techniques, just a few notes about some of the different forms of sonic or seismic energy we'll discuss. The most commonly used energy is sound waves, or P waves, or compression waves. You can see in the animation that these move as a compression and tension wave from the point of origin. And this is what we hear as sound when we speak. So techniques such as impact echo, ultrasonic pulse velocity, and sonic echo or the pile integrity test take advantage of these compression waves in various frequencies and in various simple or complex applications of the energy. The other commonly used energy is a shear wave, where the surface of a material will be moved side to side and the wave propagates as an up and down motion, the particles of that material. Shear wave energy is commonly used in techniques such as ultrasonic pulse echo testing. It's also possible with ultrasonic pulse velocity instruments to have compression wave transducers or shear wave transducers. And there's a difference in the sensitivities and the propagation speeds of these different forms of energy. So in this diagram, if we strike a surface, we're going to introduce into that material various different forms of energy. There'll be compression wave energy, shear wave energy, Rayleigh wave energy, which I'm not going to discuss today, and other forms of seismic energy carried from that strike to the surface. From that strike, we can then take advantage of different properties of those energy forms. Compression waves travel the fastest. That's why I've got Cp equals 1. And shear waves are somewhat slower. So you can see Cs equals 0.62 Cp. Practically, we can see that just by the illustration where the orange energy front is traveling faster than the green energy front. Two things to keep in mind with this. It means that when we are doing a technique such as ultrasonic pulse velocity, we would want to put sensors. It's appropriate to use compression waves because it's the first arriving energy. So if we're doing most ultrasonic pulse velocity measurements will be compression wave measurements because it's the easiest to measure. It's the first arriving energy from a transducer which puts energy into the structure. The other fact is that if we are trying to take advantage of the polarity of energy, we can do clever things with shear waves, particularly with point contact transducers. We can produce an energy front which cuts a slice through the surface. You'll see this with ultrasonic pulse echo array systems, where the results they produce are like you'd cut the side of a slab and opened it up to look inside. This is to do with a polarized property. Essentially, with point contact transducers correctly arrayed, you will have a region of tests where only shear wave energy is involved. And we take advantage of this to place arrays and to produce visual images like the one you can see here. So let's just go quickly through the test techniques I'll be discussing today. The basic plan is I'll present the techniques in brief, and then I'll provide small case studies of how they're used for different voiding and defect location applications as we go through. So beginning with ultrasonic pulse velocity, this is a time of transit measurement. We are recording as a raw measurement the transmission time in microseconds between a sending and receiving sensor, the ultrasonic pulse velocity transducers. If you look at my diagram here, I've indicated the transducers. These are 254 kilohertz compression wave transducers, and we would measure time of transit from one transducer to the other. This is converted to velocity using geometric information. So if we had placed a sending and receiving transducer 250 millimeters apart and given that information to our test device, we, in addition to our microsecond result, we have a result of speed of transmission or velocity in meters per second. This is important because it allows us to compare velocity measurements through different geometric areas, because if we then tested on a 300 millimeter section and we weren't taking that geometry into account, of course that would take longer in microseconds for the sound to transit through. The other important factor is to bear in mind the difference between a direct and an indirect transmission. A direct transmission sends the sound waves from one side or one edge of a structure across to another face of that structure. This is a knowable signal path. The sound will endeavor to, we consider the sound to take the direct path between sending and receiving transducers and conduct our calculations based upon that. We would also take advantage of this to align test areas. So we send our sound signals through the regions of concern. So through where we expect voiding might be. If you are testing a beam, you may move your transducers along that beam step by step, making sure a sound path has gone through all the regions where voiding might be expected. An indirect transmission is where the transducers are placed directly on the surface of the element, And the problem with indirect transmissions is we do not know the exact signal path the energy takes. Practically, if I was to measure a velocity through a material with 300 millimeter spacings direct, and I was to take the same measurement, 300 millimeter spacings, with an indirect probe placement, the indirect measurement would be slightly slower. We don't know the signal path those sounds are taking, and it's difficult to compare velocities between indirect and direct measurements. The next most commonly used technique, and one closely linked to ultrasonic pulse velocity, is ultrasonic pulse echo measurements. We're still recording transmission times, but now we're recording the transmission time as the signal goes from surface down to the bottom of the material and is reflected back to a receiving transducer. So again, we have a sender and a receiver, and we're recording time of transmission down and back. Typically, this is a shear wave technique to take advantage of the polarization effect I showed in the diagrams earlier. Obviously, it's particularly sensitive to voiding, like all sonic and seismic techniques are. But the reason it's commonly used for void location work is that there has been great development in tomographic imaging using arrays of sensors. So rather than having a single sending and single receiving transducer, we now have devices where sets of sending and receiving transducers are arrayed together, and they fire in sequence. The echoes are recorded and processed using tomographic techniques to produce a representation of the internal structure, showing thicknesses and targets inside, primarily voids. It'll be most sensitive to voids, but there's also some evidence of reinforcing steel and other targets within those structures. So in this example on the right here, we can see that we have tested on a step block with holes cast in and found the presence of the holes and the thickness. We've also seen a little bit of shadowing where the holes block all of the sound energy from reaching the final thickness of the block. This is a very typical tomographic image. Instruments such as ProSex Pundit Live Array or Pundit PD 8000 are an example of this kind of technique. So let's go back to compression waves, but look at a different measurement that takes advantage of this energy. Impact echo is a resonance measurement. So the previous two measurements were transmission. We either send through or bounce from the structure. With a resonance test, it's more like striking a bell or a bar of metal, where it will resonate at a dominant frequency after striking. The diagram at the top here is a graph of signal strength, amplitude, versus frequency. So we can see that the dominant frequency, shown by the strongest spike in this target, is seen at 7,000 hertz. And we've also got a thickness value we've given here of 250 millimeters. We get that thickness conversion by assuming or measuring a speed of sound to convert. Impact echo is extremely sensitive to voiding. It's one of our best tools for issues such as poor consolidation. And there's a lot of information in a single impact echo test. When we present data, and I'll show you some data later, you'll see that we normally present it either as values of frequency or values of thickness. But it's a particularly sensitive void detection tool. But does have some geometric limitations, particularly when testing elements that aren't flat and wide, like a wall or a floor. Circular columns in particular are difficult to characterize with impact echo, and measurements at the edges of walls or floors will also show additional frequency data from those edge conditions. So it's most appropriate on wide, flat areas with a consistent geometry. Slab impulse response is another frequency-based measurement, but we are going from looking at relatively high frequencies to very low frequencies. Low frequency energy on a test is primarily due to physical motion of the sensor and the structure to which it's attached. So by doing a slab impulse response measurement, we actually give a concrete slab or a wall, an almighty whack with a hammer. We have a sensor that will detect its motion held in place against that structure, and we're able to chart up the frequency of those energy again, and we're looking for a comparison between the low frequencies up to about 50 to 100 hertz and comparing those to the average frequency. Practically, we use this to determine if a slab or wall or other element, like maybe a pipe, is properly supported by the ground or earth behind it. Applications include grouting within tunnels, where they apply grout to fill between the tunnel of the rock and a concrete tunnel lining, or if a slab on ground is properly supported by that ground, or if it's been washed away through rains or other forms of scouring. Interpretation is normally done quantitatively using a ratio comparison, and this technique does call back to an American standard that defines some typical applications, particularly for testing slabs on ground. I've got a case study showing some slab impulse response data later, so that should highlight this a little more. One of the most commonly used simple compression wave test is sonic echo or pile integrity testing. With this technique, it is get a strong hammer blow, but now to the top of a pile with a sensor placed at the same place as the hammer blow. The time for that signal to travel down and come back is recorded and visually measured. This is most commonly used to determine approximate lengths of the piles and also to determine if there's any defects along the length of those piles. This is not going to be something I discuss too much because I'm not talking about foundations today, but this is a very commonly used seismic technique. Now, just before we continue to the case studies, I want to take a moment to talk about ground penetrating radars. Anyone here a ground penetrating radar user? Again, you can respond in the chat or you can unmute if you would like. So if you've got Goldie responding, anyone else? Karen? No, that's great. Chris, and again, feel free to chime in audibly if you'd like. What's been your experience using radar tools for voids? What they're good at, what they're bad at? I'll give my view in a second, but I'd like to hear some feedback from the audience before we go on to look at how it can be used for voids and consolidation and other work. So again, so we got Goldie saying that you need to be able to see the speed of the wave through the layers to actually tell where a void may be. That's actually very, very good feedback. Anyone else or anything else to say? Again, you're quite welcome to talk as well as just post in text. I'll read out anything that comes in by text though. Okay, I'll keep moving, but that's a good starting point, just where you need more information, where it's not as straightforward as locating an embedded reinforcing bar, post-tensioning, or even something like a slab thickness. We've also got Mark saying that reinforcing may hide voids below, and it's quite right. Essentially, radar is most sensitive to steel. When we reflect radar energy from air, which might be the thickness of the slab or a void within the slab, we only get about 30% of the energy back. If we reflect that same radar energy off steel, such as reinforcing steel, we get all of the energy back. That's why you get a hiding effect, where if you've got a lot of steel above something, you may not be able to see through that steel to what's behind. Well, you can't see behind it, but it creates a shadowing effect. So that's our first limit. The other limit is, unless the geometry is really clear, something like a polystyrene void former, you don't necessarily get a reflection from voiding in concrete with a ground penetrating radar. The more common effect, if you've got voiding above the reinforcing, is that it may be shown as a reduction in signal strength. As you can see in the example here, we've got a sort of graying in the middle of the image, and the depths are also a little bit lower for the reinforcing in the middle of the image rather than towards the edges. So it's not something that you could interpret as clearly as the position of a reinforcing bar. It actually requires quite a sensitive eye or a computer sort of quantitative processing approach to find these regions of reduced signal. And of course, if you need to have a signal to compare, so you are limited very much by where you're able to measure. But it's got to be good for something. People are using radar all the time, and it's true. A fairly common application for radar for void location is specifically voids underneath a slab. So in this example, rather than looking at what's happening up at the level of our reinforcing, we're now looking at the reflections from the bottom of a slab on ground, and cast in place have been some polystyrene voids to simulate lack of support. The signal from these voids is quite a bit stronger than the same signal from the reflections from the bottom of that slab. And this is a pretty characteristic response. It does require gain settings to be correctly set to be able to compare strong to weak reflections. But this is something which would be a normal task for radar, is to look for the strength of the signal coming from the thickness at the base of the slab. And looking for stronger signals from air rather than ground connection. There is a standard which relates to degradation of structures. The standard is ASTM D6087, standard test method for evaluating asphalt-covered concrete bridge decks with ground-penetrating radar. This is the quantitative approach I mentioned. They compare a signal strength of the amplitude from reflections from reinforcing, with the intent that where you have an average signal strength determined over the whole of the structure, and you have regions of lower signal strength, that indicates potential regions of degradation. And that would get plotted out by doing large surveys. This is most commonly used for bridge decks, of course, or structures which are maybe exposed to salts in America and are at risk of expansive corrosion of the reinforcing steel. And the degradation effect essentially is caused by some combination of physical damage, the presence of salt and corrosion product around the reinforcing steel affecting that signal, and differential levels of moisture around that reinforcing steel, all of which will have an effect on the signal strength of those reflections. So there is a standard. It's not something you would really want to be doing by eye. The effect is fairly small, but with large data sets and actually analyzing those numerically, there is some scope for that. But there's some other points where radar can be appropriate. I'll mention these as we go through the case studies. Finally, this is a good moment just to discuss the depths that each technique can work to, because if you're choosing techniques, you may have a structural area that you need to get through. So the technique of ultrasonic pulse velocity, that's our point-to-point transmission measurement, that's limited to, not very limited at all, 5 meters or more penetration from sender to receiver is achievable. Ultrasonic pulse echo testing, you're going to find that different devices have different limits. Probably the thinnest penetration is around 0.5 meter, with as much as 2 meters or more with commercial systems. Researchers have gone quite a bit deeper, but they're doing rather more involved arrays, rather more involved techniques. The impact echo technique is appropriate down to 1 to 1.5 meters for thickness determination and voiding close to the surface. You'll find it's more difficult to find voids directly at the bottom of a thick structure, though that's less of a problem for normal slab thicknesses, 100 to 300 millimeters or so. The slab impulse response technique is very limited by thickness. Because we're hitting a flat plate of concrete and trying to get it to vibrate, we have a maximum of thickness where that stiffens it up so much it will no longer move under the hammer blow. And we'd call that around 400 millimeters. So if you're assessing if slab impulse response is appropriate, you wouldn't want anything greater than 400 millimeters, because that would control the test more than any structural support behind the slab. Pile integrity testing, you have a depth to diameter ratio limit of around 20:1 or 30:1, depending upon the surrounding soil. And ground penetrating radar equipment, you'll find your maximum penetration on ProSec scanners is around 700 millimeters, others may be around 500 millimeters. And your utility location scanners is going to be more like 1 to 5 meters depth, depending upon the soil conditions being scanned with, and how much moisture is in the ground. So let's start to go through case studies. Let's begin by looking at the very simplest void, which you may not think of as a void, which is an actual thickness of a structural element, because it's a large amount of air existing at some point beyond our concrete. The techniques of impact echo and ultrasonic pulse echo, they're a single-sided measurement. So if you've got unknown slabs on ground or structures where it's hard to determine the exact thickness of, they can be appropriate. Ground penetrating radar is more and more useful for structural thicknesses as well. Now, all of these techniques, I stress, you are going to need to calibrate based upon some physical measurements or some speed of sound or speed of radar transmission information. And one defect that could be a thickness measurement to keep in mind is when you're looking at structures like waffle slabs or pod slabs, where there's polystyrene void formers forming thin slab areas, then thicker beam areas, which are poured in situ. These techniques could be appropriate to determine that the void formers have not moved or changed. Now, so let's look at some data from a couple of different test techniques. This is impact echo test data. This was taken on a boat ramp for a case study. So we have color-coded on the left here a thickness of around 500 millimeters, and then our thickest is around 650 millimeters, each square being an individual impact echo test like this. So we've charted those thickness values, giving us the thickness of that boat ramp. This is the same boat ramp when measured with an ultrasonic pulse echo technique, where it's, it's not the same boat ramp, it's another example of a structure with thinner and thicker regions, with the dark areas being 200 and the thicker areas being as much as 600 millimeters thickness. So while this is the same format of data, one is the resonance test, the other is the direct echo from the back surface test. Finally, we can come back to our ultrasonic pulse echo data, where something really important with ultrasonic pulse echo data is it's much more useful when you have a thickness measurement, because thickness measurement actually allows you to do the structure. So in this region, it's actually finding defects, and we've relied upon these locations of thickness, which vanish when we have air above them, voiding above them. So it's always good with ultrasonic pulse echo techniques or impact echo techniques to have them respond to thickness, because if you lose your thickness measurement, that can be a strong indicator there's voiding or something else in the way. This is so going on to probably the most tricky to measure form of internal voiding of a structure, let's talk about consolidation. So going on to poor consolidation or honeycomb voiding, this is one of the most difficult to locate forms of voiding, because it can be quite distributed. And so our echo techniques tend to not always get a clear reflection from honeycomb voiding. Ultrasonic pulse velocity can be a very good technique. We get a very apparent slowing of pulse velocity signals through regions of distributed voiding, maybe 10% or so reduction in speed. Impact echo is particularly sensitive. Its resonance-based technique has the advantage that anything in the field of impact of that measurement, maybe 10, 20 centimeters around the impact point, a little bit more if it's a thicker element, is going to control the resonance of that test. So I found impact echo to be particularly good if you're looking for small voids in a slab or wall. Again, columns are possible, but more difficult to work with. Ultrasonic Pulse Echo is less sensitive, but if you have a good thickness reflection, it's quite characteristic for that thickness reflection to vanish as the voids interrupt the shear wave energy traveling from the surface. So I've got a picture of that in a second to show you. So pulse velocity or impact echo, they're the most likely tool for this sort of location. Pulse velocity, we find it as reduction in speed. The key thing to know with pulse velocity is the signal path has to be through the voided region. You can't rely upon being even a little bit distant from it. So you need to be quite careful and precise in setting up test plans with pulse velocity to send the energy through the regions of the void. Impact echo, the test will respond through frequency shifts for light amounts of voiding. So what's quite common is a red shift. It's a lower frequency measurement. This is because the voiding essentially makes the element more hollow. So if we were interpreting that data as frequency, maybe we shift from 7,000 to 5,000, or maybe a thickness measurement of 250 might change to around 300 millimeters if we're presenting data as that. What you obviously can see here is that pulse velocity and impact echo, it's quite important that you have large data sets or moderate sized data sets so you can compare the average results in velocity or frequency to specific areas looking for changes from those average results. Now, delamination, this is probably the easiest form of void to detect. Now, by delamination, I particularly mean a flat, wide separation inside a concrete structure, such as might be caused by expansive reinforcing corrosion, cold joins, or some other sort of shattering that separates plates of concrete. If we can put any sonic test to pass its energy through the regions of that delamination, it will slow it down for UPV or reflect that signal back to us with pulse echo, or really affect the resonance measurements with an impact echo test. Now, the access is still important. You still need to be able to put the sensor on top of the delamination. So in a region like this, you might not be able to test for delamination at areas like that. So this is an example of a particularly difficult to detect delamination where expansive corrosion has spalled away a section of concrete on the underside of a concrete deck, exposed to salt water underneath. So in this particular example, we have that very characteristic thickness echo loss when testing over that spalled region. So it's always good to be looking for thickness measurements when you are using any sonic or seismic technique, because that gives you another point to look for change as well as direct reflections in the measurement. Now, void formers, again, it's just like a thickness measurement, which means that even the relatively insensitive ground penetrating radar can be appropriate. UPV, impact echo, again, access limits. So large voids are going to behave similar to a void former. So if you have a great big area where there is no concrete filling it, like it was maybe held by overly dense reinforcing, you may be able to look for responses like this. So techniques like impact echo can now show a thinner measurement, a higher frequency measurement, if the void is sufficient to essentially separate that into a thinner slab. And again, we see a slowing of results for impact echo. With the caveat, as always, ultrasonic pulse velocity measurements have to go through the regions of void. Finally, these larger voids are the most detectable with ultrasonic pulse echo because you will get a visible response to large voiding, and you'll also have those large voids interrupt the thickness measurement of the ultrasonic pulse echo techniques. We've discussed subgrade voiding, so slab impulse response is very sensitive. Impact echo, it will not work. To an impact echo test, a concrete slab placed on earth or a concrete slab placed on a void is identical because we're using high frequency sound energy to measure resonance. It'll resonate the same way on ground or off it. So this is one particular tool that people often think to use, but is not appropriate. Now, you certainly can use ground penetrating radar, and for subgrade voiding, it's very common to combine an approach of ground penetrating radar and slab impulse response for the best measurements. So in this case study, the left-hand data is the signal strength at the thickness of a spillway underneath it, which lets water out of a dam, indicating regions of stronger signal. The color map data is slab impulse response data, showing higher mobility of those measurements. And the white circles indicate regions of actual voiding. So, and the picture shows a drilled core from that. Now, cracking is one of the questions I get asked most commonly, and it's also one of the things that's hardest to do a lot with. If it's parallel to a sensor, it's a delamination. You can measure it like you would measure a delamination. If you've got a horizontal crack visible from the surface, it may be appropriate to use one of the ultrasonic pulse velocity-based measurements of crack depth. These are geometric. They're not like critical crack depth measurements for ultrasonics used with steel. So they're maybe not as precise. There's no test block set to make those measured values precise, but there is an indication of depth, particularly is it big or is it small? And if there's a lot of distributed cracking, it may affect an impact measurement. It may affect a UPV measurement. But ultimately, that's the hardest thing. You have a great deal of difficulty finding cracking with any technique, ultrasonic, radar, or other, when the geometry doesn't put that crack flat against the face of the structure as a delamination. So pulse velocity has been used for crack depth measurement. These are based on a British standard that actually defines a trigonometric relationship, essentially triangles, for crack to assume the signal has to travel all the way to the bottom of the crack and then around it. So there's several assumptions embedded, but instruments like ProSex Pundit, PL, and the Surfer do have crack depth measurement modes, and they're useful, even with the limitations of that technique. The final kind of void I want to show a small case study of is grouting defects. So it may be in a conduit, post-tension duct. It may be between joins. Impact echo is sensitive to voiding in ducts over which tests are conducted, and ultrasonic pulse echo is sensitive with a different reflection from a duct that is filled rather than unfilled. But it's hard to characterize that reflection only on signal strength. Phase analysis is very useful. If you're looking at grouting separating at joins, that would be similar to a delamination. And a common technique is to look at grouting behind slabs, such as grouting to restore slab support, using the same techniques of ground penetrating radar and slab impulse response. But particularly, let's look at some small examples of voiding, in this case, rebar ducts. This case study, with the kind of precast wall element that we were testing is defined by AS 3850.2, where there is reinforcing bars that tie a wall together, where each panel of the precast wall is grouted at the join and grouted in ducts that hold reinforcing bars that tie it together. The potential defects we are looking for are those occurring within the ducts. And we did that using ProSex Pundit's PD8000 array, where we collected measurements over the ducts. So we'd get, as a typical reflection, a reflection from the duct and a secondary reflection from the thickness of the slab with a bit of shadowing underneath. One interpretation we could use is we could look at the strength of this reflection, but the particular post-processing we did with Pundit Vision software, it used to be known as Intersaft, was to process for signal phase. If you're not familiar with the phase of a signal, I can point you to a presentation which goes into this case study in more detail on one of our previous newsletters. But essentially, the waveform of a sound wave or a shear wave sent into a structure is going to come out with a certain positive or negative position. And it's going to reflect back either with the same positioning or with a slight change, even though it travels at the same speed. By measuring the phase of this in degrees, we can actually distinguish between a reflection of shear or sound energy from a void to that of the signal from a metal bar properly grouted into a duct. So in this particular study, the duct is filled and known to be checked by drilling. And we start by looking at the phase of the reflection on that duct around 101 degrees. We can then look at the phase of the reflection from the thickness of that wall. That thickness is an air interface. So now we have a phase of minus 110 degrees. So we can see that we've got a difference in phase between those 2 points of about 220. The theoretical results would be about 180 difference in phase. So we can see we've got a distinct visible difference, which we've color-coded here in the phase of a steel duct with proper grouting, a steel bar in a duct with proper grouting, essentially steel in solid material, and the interface between that solid material and air. So now we can do the same interpretation looking at the ducts themselves. So this is a vertical duct in the precast panel. So we have a red phase and a duct that has been filled. This was prepared for the test. It was one where grout had been correctly filled in. We can see that we have a reflection, a purple color coding, indicating red to purple is around 90 to 180 degrees positive phase. Then we can see that continuing on a separate section of that same filled duct, we have a positive phase, red color indicating, again, that 90 to 180 degrees. On a duct which has had no grout pumped in at all, we are now moving to a green reflection, seen here, indicating a minus 45 to minus 90 negative phase. So we can see in that case study, we've correctly differentiated grouted ducts from ungrouted ducts, both with rebar inside, based upon the phase of the reflection. This is an interesting case study. There's a better presentation of this on our previous newsletter, and I'd be happy to discuss that in more detail with anyone who is particularly looking at doing this kind of investigation on rebar ducts or post-tensioning ducts in structures. Anyway, that concludes today's presentations. Thank you so much for joining us. I'll finish up my recording for the moment.